Okay. I think it's probably worth just doing one more example of a proof using the kind of rules of inference that we've looked at in the last one. So I have another example, but before I do that, I will just recall one property of the real numbers. So this is something which you can work out by thinking carefully about decimal expansions. One more example of inference, or just using standard methods of proof, I suppose, without trying to vary the way that we go about it. Note that in the real numbers, if x, y, z are real numbers, then x is less than or equal to y implies that x plus z is less than or equal to y plus z. It's pretty easy to see this just by thinking about what happens if you're on a number line. If I take x less than or equal to y, whatever distance these are away from each other, if I then add some constant thing to it, I'm just going to move them up by a bit, and so they will still be in this relation to one another. Or even if I take z to be a negative number, they'll just move downwards, but they'll still be in the same relation. As I say, you can prove that carefully if you think about that decimal expansion, but it would take a bit too long to worry about that. So that's going to be one property I'll take as a basic property. And if z is bigger than 0, then multiplying by z is going to stretch things out. So x less than or equal to y implies x times z is less than or equal to y times z. And that's going to be another property I can call dagger. Okay, so let's have another theorem. And this theorem is going to be, this time I will have a hypothesis, so I'll write it like this. For all x, for all y, for all z, for all w, x less than or equal to y and z less than or equal to w, this being true is enough to tell you that you can basically add the two bits together. So x plus z is less than or equal to y plus w. So go straight in with a proof. I'm not going to be very careful about telling you when modus ponens is being used, but you can go through and see that it's it's all the way along the line we're using it. The first thing to do is to use the property that we've got here, star. So from star, x less than or equal to y and any z in R. Already I'm going to use a modus ponens. From that I'm going to deduce x plus z is less than or equal to y plus z. Okay, so that is good. And then I want to do a similar thing by just looking at what happens by adding want to get from y plus z to bigger than y plus w. So since I have from z less than or equal to w, so this is my assumption, the hypothesis I'm using, we can deduce that adding y to both sides, y plus z is less than or equal to y plus w. Okay, and now I've got these two statements. So I've got one number less than another, and then that number less than a third, and then from transitivity, and I'm going to use modus ponens again because I've got a particular case that I'm looking at. Then I can put these two together. We deduce x plus z is less than or equal to y plus w. And that is a statement I wanted to prove, and so I can give myself a QED, that's quodere demonstrandum, square at the end to say I've done it. Okay, excellent. So that was the one more example. Sometimes you want to prove that statements are false. So it may very well come to situation in mathematics. Someone has put forward a conjecture about what's true, and you want to say that it's false. And if the statement is of the form for all x something is true, then you want to say that it's false, then you want to produce an x for which it is not true. So counterexamples. So this is a nice use of some of the negation rules that we looked at last time. To disprove a statement of the form for all x, p of x is true, we need to prove that it's, so if we want to say that that's false, we need to prove that not of it is true. So not of for all x, p of x is true. And we know that there is a way of moving this not through the quantifiers if we can swap them. So this is equivalent to there exists an x such that not p of x. And that is the basic idea for disproving statements of this particular form. So let me give you an example, and then we will probably finish there, I think. So let's take the statement. So the example I'm going to take is 622 from the notes. So let's disprove for all A, B and C. We'll take those subsets of some universal set U. A intersect B union C is the same as A intersect B union C. Okay, so if that's what we want to disprove, let's first have a think about what this is saying. So if we take a Venn diagram to help us think about this, that would be a good idea. So these are my A, B and C, and I want to take the intersection of A with B union C. So that's all the stuff that lies in B or C or both and A. So that's the left-hand side. And the right-hand side is going to be A, B, C. So I'm going to take the intersection of A and B, and I'm going to take all of that intersection together with anything in C. So I get all the stuff I got before, but I get a hell of a lot more. So if I can just pick the right examples here, then I can make sure that this is going to be not true. So what if I just make BB completely trivial, and then I can just see that the A and the C bits are going to go wrong. So let's take let B be the empty set. And if I do that, then I just need to prove that A intersect C is not the same thing as A intersect the empty set union C. So we'll take B to be the empty set, we'll take A to be the empty set, and then we'll take C to be a set containing 1. Then the left-hand side is B union C is C, and A intersect that is just the empty set. And the right-hand side, A intersect B, I'm just getting the empty set, union C, that gives me 1. And they are not equal. So this is a counterexample. Okay. Now, if you ever have to give a counterexample, you want to give the simplest one you can think of, but it's a bit more elegant, but you can give anything you like, as long as it is something that refutes the statement that you're trying to make. So we started with for all A, B, C of a certain form, something is true. If I want to negate that, then I want to say there exist an A, B, and C such that this is not true. And that is exactly what this does here. So that's the idea of counterexamples. And we'll probably pick up, that's probably enough for this week, so we'll pick up proof by contrapositive and the other things next week.